Okay, let's get started, please. Let's get started, please. I'll be impressed if anybody can tell me what we are doing and where we were.
Single value decomposition.
Singular value decomposition. So singular value decomposition. And what had we gotten? What have we gotten? Does anybody?
We're trying to prove something.
Trying to prove something. Yeah. Well, we're trying to prove that everybody has a singular value decomposition, right? That theorem, every matrix A can be expressed as U sigma V transpose, right? Where U is an orthogonal m by m matrix, V is an orthogonal n by n matrix, and sigma is a matrix consisting of, it is a m by n matrix where you've got a diagonal matrix on top and then 0 below. Diagonal matrix on top and 0 below, and the sigmas, the diagonal entries are decreasing, and they're all non-negative. Okay, these guys are called the singular values. The singular values in the singular value decomposition. Okay, so we're trying to show that everybody can be expressed like this, and this thing has a lot of applications. Now, the harder question is, where were we? Where were we? Because the story was pretty intricate. We had gotten. Does anybody remember? We had gotten the compact, right? We had gotten the compact singular value decomposition, right? We've gotten the compact singular value decomposition. A equals U1 sigma 1 V1 sigma 1 V1 transpose, right? Where sigma 1 was the square roots. Sigma 1 was the square roots of the eigenvalues, the non-zero eigenvalues of ATA, right? The sigma I from 1 to R, were the non-zero eigenvalues of ATA, right? And what was V1? Anybody remember what V1 was? V1 was the left half, the left part of V. Recall that we had this vector, we had this matrix V, and we split it into two parts, V1 and V2. Right? This was a orthogonal n by n matrix, right? And does anybody remember what V was? What was V? V was the matrix the orthogonal matrix that diagonalizes ATA. Okay. Remember, ATA is symmetric. ATA is symmetric, so it's orthogonally diagonalizable, right? So V was the orthogonal matrix such that V transpose ATA be equal lambda 1 through lambda n. This thing here is sigma 1 squared. Right? These guys are all 0. Okay, remember, R was the number of non-zero eigenvalues, right? And this thing was an n by R matrix. V1 was the n by R matrix consisting of the eigenvectors corresponding to lambda 1 to lambda r, the non-zero eigenvalues. Okay, it's worse than a novel, right? You have to remember who everybody is. Right? Okay, it's not worse than a novel, right? I'm sure that you've all read some Russian novel which has so many characters that you have to remember everybody. Okay. What?
All the names end in ski.
Yes, yeah, right. This is no worse than that, I hope. Okay. So and one more character. And U1 was a V1 sigma 1 inverse. Right. U1 was taken to be a V1 sigma 1 inverse. Okay. Right. Okay. So that's the last character of the story so far. Okay. So altogether, we had this thing: A equals U1 sigma 1 V1 transpose. Okay. And we're hoping to get the full-blown singular value decomposition, but we just have sort of parts of it. This is not a square matrix. This is not a square matrix. Right? These guys aren't square matrices. They're not. We want square orthogonal matrices on both sides. We don't have them yet. We've got something pretty good, but it's not complete. Okay, so we're gonna basically change this so that it turns into U sigma V transpose. Okay, we're gonna mess around and see that this thing can be expressed as something like this. Okay. So what we're going to do is we create U as follows. Okay. The V that we're going to replace this with, we already have. That V that V1 was part of, we're gonna use that. We'll use that V. Okay. The sigma 1. It's easy, we just extend it, we just make it bigger, it becomes the sigma. The thing that we're lacking is the U, so we're going to make the U, we'll build it. Okay. So first notice that U1 consists of orthonormal vectors, orthonormal columns. U1 consists of orthonormal columns. Why? Now let's think about it. U1 equals AV1, so A V1 sigma 1 inverse. Right, this is V1, this is sigma 1 inverse. Okay. Okay, now I'm just going to multiply this out. When you multiply this out, you get AV1, AV2, dot, 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 AVR. And when you multiply by this thing, well, each column gets multiplied by the corresponding number. Okay, so this is just multiplication. We're looking at what U1 is. And we're trying to see that the columns are actually orthonormal. They're orthogonal to each other, and they're a norm 1. Okay, so let's call this U1, U2, UR. Okay, and then think, what's U1, UI transpose UJ, right, the dot product. What is that? Well, by definition, it's going to be A BI over lambda i's to the 1/2 transpose times A Bj over lambda j to the 1/2. All right, well, what's that? These constants we can pull out, right? So it's just going to be 1 over lambda I to the 1/2, lambda j to the 1/2. And then we get the transpose of AVI. Well, the transpose of a product is the product of the transposes in the reverse order, right? Right, so we get VI transpose, ATA, VJ transpose. Right? Okay. Well, what's ATA VJ? The VJ, remember, was an orthonormal basis of eigenvectors, right? These were the V's. V was the matrix that diagonalized ATA, right? Right. So these guys, the VJ, recall, were an orthonormal basis of eigenvectors of ATA, right? Because they're from the matrix that diagonalizes ATA. Right? Right? With eigenvalues lambda 1 through lambda r. So this is just going to be lambda j vj, right? It's just an eigenvector, so you get lambda j vi transpose vj over lambda I to the 1/2 lambda j to the 1/2. Okay. Okay, but what's VI transpose VJ? So you know, product of VI against VJ, and it is equal to 0 if I is not equal to J, right? So equals 0 if I is not equal to J, and this thing will be 1 if I equals j, right? Because they form an orthonormal basis, right? And if I equals j, over here you get
It will be
lambda j
over lambda I
over lambda j again. Right, you get lambda j square root times lambda j square root, which is just lambda j. So you lambda j over lambda j, that's 1. Right, if I and j are the same, then this bottom is just going to be lambda j. Right, so you get 1 if I equals j. And that tells you that the U, this matrix, the columns of U1 are orthonormal, right? That they're orthonormal to each other because the dot products are either 0 or if it's against itself, it's 1. Okay. So that's what we've just shown. That UI consists of orthonormal columns, which is good because we wanted an orthogonal matrix over here, right? We wanted an orthogonal matrix over here. Right now, what we have is an M by R. Right now, what we have is an M by R matrix. We want, but at least the columns are orthonormal. Okay, the columns are orthonormal. Okay, so.
That's a question really quick.
Yeah.
So just for why is A transpose A equal to the eigenvalue?
Yeah, so just remember what the V's are. These columns Vj's. These are the columns of the V matrix. Right, these are columns of Vi. These are the columns of V1, which come from the V matrix. Now, what was the V matrix? The V matrix was the thing that diagonalized ATA. If it diagonalizes ATA, that means that its columns are eigenvectors of ATA, right? So the columns are eigenvectors. So ATA Vj is just going to be lambda j Vj. Right? Okay, so what we see is that so U1 through UR are an orthonormal basis of the range of A. Right. So, and first what we see is that they are orthonormal. Right. That's what we've just seen. That they're orthonormal. Okay. Since they lie in the range of A, right? Each of them is A times something, right? Each of them is A times something. So all, right? Since all UI are in the range of A, which has dimension R, we see they're an orthonormal basis of the range of A. Yeah.
What's the range again? What is the definition of that?
It's the column space. The column space. Or another way of thinking about it is it's everything that looks like this. Right? It's everything, A times anything, like the outputs. Anyway, it's a column. It's the column space of A.
Wait, how do you know the dimensions are?
We did that last time. Do you remember? It was when we took the, right, when we, R was the number of non-zero eigenvalues of ATA, remember? Right? R was the number of non-zero eigenvalues of ATA. So since ATA is symmetric, the rank of ATA is R. You said this.
Yeah.
Okay, and then we had the warm-up exercise. Remember the warm-up exercise at the very, very beginning, where actually we did it last Friday, so maybe you've forgotten. But we had the warm-up exercise that the rank of A was the same thing as the rank of ATA. So.
Did we say that R could be 0 though, or could that be no non-zero eigenvalue? Or wait, no, never mind. Sorry.
It could, but then you would have the zero matrix.
Yeah. Okay.
Yeah. Okay. Let's get back to the story, right? We've just seen that the columns of U1 are an orthonormal basis. Okay, right? And remember what we're trying to get? We're trying to get a full-blown orthogonal matrix, right? Okay, so what we do is we say, okay, use Gram-Schmidt orthogonalization to extend U1 du-R to U1 through UM, an orthonormal basis of Rm. Okay, remember Gram-Schmidt orthogonalization, right? You can make an orthogonal. You can make an orthonormal basis from a regular basis. So you take this basis, extend it to a full basis, and then use Gram-Schmidt on it to get an orthonormal basis. Okay. Just a remark. Notice that these second guys, UR plus 1 through UM, are an orthonormal basis of the range of a perp. The orthogonal complement of the range of A. These guys are an orthonormal basis of the range of A. The remaining guys will be an orthonormal basis of the complement of range of A, which by the fundamental subspaces theorem will be the null space of A transpose. Okay. I don't know if we're going to need this remark. I sort of ran out of time in the first class before I could use it, so I just leave it on the sign here. Okay. Okay, but in any case, yeah, I showed the first class a movie, including the Singular Value Decomposition song. I think I'm not going to show you guys that. If you want to look it up, look on YouTube for SVD song. Just for entertainment. You guys don't get the entertainment. Okay. Okay. So now we've got an orthonormal basis, right? So let U be U1 through UN, right? Now that gives us our square, the square matrix that we wanted. Right? These guys are the columns. These guys are the columns. Okay. Where this thing was what we were calling U1, and we're going to call this thing U2. it's orthogonal, because we just made it to be orthogonal. Okay. Okay, so now so let sigma be the m by n. Let sigma be the m by n matrix where we have sigma 1 here, and then everything else is 0. Okay. Right. Remember what sigma 1 was, right? Sigma 1 was the square roots of the non-zero, the R by R matrix, which was the square roots of the non-zero eigenvalues of ATA. Right, which we're also going to denote by these values we denote by sigmas also. So sigma 1 for sigma R. Okay, so claim that A actually is U sigma V transpose. We have our V from before. We've just finished making the U, and we make our sigma just by fattening out the sigma 1 so that it's the right size. It was R by R. We now make it n by n. Okay, so let's see that that works. Well, U is U1, U2. Sigma is sigma 1, 0, 0, 0. And then V transpose, remember what V was V1, V2. So V transpose is going to be V1 transpose, V2 transpose. Okay. Now, when you multiply matrices in blocks like this, it basically multiplies in those blocks. So what you end up with is sigma 1 V1 transpose plus 0 V2 transpose. And you get 0 V1 transpose plus 0 V2 transpose. Okay. Let me make it simpler by making these zeros just 0. So I'm going to put the 0 here. And this is also 0. Should I keep it? Maybe keep on copying 0 V1 transpose plus 0 V2 transpose. In any case, this is all 0. The 0 matrix. Okay? But, so what do you get? When you multiply these guys, then you get U1 sigma 1 V1T plus U2 times 0. But that's a compact singular value decomposition, right? That's a compact SVD, and so that equals A, right? So U sigma VT equals A. so we see that every matrix has a singular value decomposition. Yeah, Mariah.
Wait, why don't we just find the compact
Why don't we just find the compact one? Yeah, the compact one actually contains much of the useful information. Okay, but you'll see that the full-blown one we can actually use to get some. We can use it to get some useful result.
Okay. Even though they're equal, like the compact one equals the full-blown one.
Yeah, they're equal. It's just a different expression.
So the other one has zeros.
Yeah, like this one has more zeros in it. This one has more zeros in it. This part is orthogonal. These things are orthogonal. You'll see. Just wait. Okay, everybody all right? Great. Okay, so, okay, great. So, I don't know if I want to do this. Let me quickly sketch out the procedure. Okay, sketch of procedure that we just went through to create the SVD. Okay, so the first thing you do is find the orthogonal matrix such that you find the orthogonal matrix that orthogonally diagonalizes ATA, right? So in other words, one orthogonally diagonalize ATA, right? Right. And then two construct U1 as a V1 sigma 1 inverse.
Wait, does that say the negative one there? Or is that a what?
Where?
With the sigma?
Sigma 1 inverse.
Okay.
Yeah, sigma 1 inverse. Okay, so maybe let me be less sketchy. So remember that D is lambda 1 through lambda R, and then a bunch of zeros afterwards. Okay, and then this guy here is sigma 1 squared. Right, the square root of that diagonal matrix is sigma 1. Okay, so the two construct U1 as a V1 sigma 1 inverse, where V1 is the first R columns of V. Okay, and then the third step is to complete a U1 to U by Gram-Schmidt. Right. To make the remaining columns, right? This guy is only M by R. You need M minus R more columns, right? So you complete it using Gram-Schmidt, and then that's it, right? So then A equals U sigma U transpose. If you go through the proof, you'll see this is what we did to get it. about 10 minutes. Okay, so let me say a couple of things. Singular vectors. So here's the definition. The uj, the columns of U are called the left singular vectors. The columns of V are called the right singular vectors. Okay. Okay, so let me think of what I can say. Give me 1 second to think. Okay, let's do that. Okay, so observe. So there's actually a relation. There's actually a relation between the left and right singular vectors. A B equals U sigma, right? Because A is U sigma V transpose, but V transpose is V inverse, right? V transpose is V inverse because V is orthogonal, right? So you multiply by V on both sides, and you get AV equals U sigma times I. Okay. So what does this tell you? This tells you that A Vj, if we look at the columns on the left side, so considering the columns, column-wise, this says that AVI equals sigma I UI. For I equals 1 to n. Right, so there's actually a relation between the left singular vectors and the right singular vectors. Right, if you have the right matrix, you can make some of the left matrix. Okay. Also, if you take the transpose, you get A transpose U equals V sigma transpose. Right? Just transpose the singular value decomposition and then multiply on the right by U. Right? A is U sigma V transpose. A transpose is V sigma transpose U transpose. Right? So multiply on the right by U and you get this thing. Right? And what you get is that A transpose Uj equals sigma j Vj for j equals 1 to n and equals 0 for the j bigger than that. So there's some relation, and you can use this when you're doing the singular value decomposition. You can use this fact. This fact is you could use it to create your U. If you have the V's already, you can create the U's. Right, so here, the first thing you do is you get the V, right? So you have the V's already, and you see that you can get the U's. You can get the U's from the V's. Okay. The last thing I want to say is the most important in terms of application. Something called the outer product expansion. The outer product expansion of A. Okay, so A is U sigma V transpose, and I'm going to group it like U sigma V transpose. Now, note the columns of A, the columns of U sigma are sigma 1, U1, sigma 2, sigma 2, U2, sigma n, UN. Okay, and of course the rows of V transpose are, V1, V2 are the columns of V. Okay. If you multiply these two things together, right? These columns and these rows, what you get is that A equals sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus sigma n UN Vn transpose. This is something called the outer product expansion. We skipped it earlier. I'm sorry, a little bit sorry that we did, but anyway, this is what it is. Okay. If we take for some k less than the rank of A, the first k terms in this expansion we get what we get is we get this, of course, the sum of the first k terms. But what it turns out to be is U times a sort of truncated version of sigma times V transpose. If you think about it, this is what's going to happen, right? What's going to happen is you're going to get the singular value decomposition, but with only the first k terms. Only the first k singular values will show up, which is a rank k matrix. It turns out that this is the rank k matrix closest in Frobenius norm to A.
Or would you write in parentheses then?
Yeah, so it says in Frobenius norm, which you probably forgotten, or I may have never said what it was. But we saw it. Do you remember when we talked about the norm of a matrix? You just take the sums of all the entries squared to the 1/2. You pretend that the thing is a giant vector. You pretend the matrix is a giant vector.
Okay.
And you say, well, the norm is just going to be the norm as a giant vector. That gives you a distance. That thing is called the Frobenius norm. Okay, so it's saying that if you look at this matrix, it's actually the closest rank K matrix to A. It's like the method of least squares thing, right? You look at the space of rank K matrices. You've got your matrix A, and you find the guy who's closest to A with respect to this Frobenius norm, which is the method of least squares. And it turns out that this thing is the best rank K, or a best rank K approximation. Yes?
So is this what we use to do the image?
This is what you use to get those images, right? Like, so if you have an image and you want to find a low rank approximation of that image, this is what you do. You take if you say, I'd like to have a rank 15 approximation of my image, you get the singular value decomposition, and then you truncate the singular values to the first 15 and make the rest zeros. This will give you your rank 15, give you a rank 15 matrix, and there's this theorem that we're not going to get to that says that that's actually the best one. Okay, that's it. That's the end of the course. Thanks for what I hope was a fun term. It was fun for me. I don't know what for you. Okay, so yeah.
Will we have a review session on Friday?
Yeah, if you want. People want to have a review on Friday. Okay, so I'll be here on Friday. I mean, yeah. I'll be here on Friday. We can have a review.
Sweet.